All right. Howdy.
Howdy, howdy.
Good afternoon, y'all. Happy Monday. Thank y'all for being here. Hope y'all are doing well and that you had a good weekend. Um, Friendly reminder, I don't know if you saw the email, but I posted the grades for quiz one and quiz two, and then also on our Google Drive, I posted the solutions to those quizzes. It contains a solution as well as the rubric. If you missed points, I'll pass those quizzes back at the end of class so you can see what you might have missed points on. You can see the rubrics to know what the correct answers would have been. And if you have any questions about any of those things, feel free to let me know. Um, in general, quizzes will be pretty similar to the two styles of quizzes that you've seen, where it'll either be like kind of a short application based on some math that we've already seen in a previous class, or definitions that we've already seen, or like kind of maybe a combination of the two. Um, so if the quizzes aren't going well, make sure we're reflecting on the things that we're missing so that we can use that to reinforce our study habits so that we can do better on the next ones. Um, Last time we derived the one group diffusion equation, and we talked a little bit about the conditions that are required to solve that equation. And so that, if just as a refresher, this was the one group diffusion equation. Um, we had said last time that if you look at every term, so like there's four terms in this equation. Every term has units that are some kind of neutron rate density. So they have units of like neutrons per unit volume per unit time. Um, and we can like assign definitions or like physical meanings to each of these terms depending on what quantities are being described within the term. So the d by dt term is your rate of change term. That's the rate of change of the neutron density. The term that has the Laplacian in front of it, that came from our net leakage term. So that's the net leakage rate density. The term that has the nu f and the sigma f in it, those are quantities that tell us about the number of neutrons emitted per fission and our fission cross section. So that term is the production rate density. And then the last term, which has that sigma a on it, would be the absorption rate density. So that's what the equation is. This is a very useful equation to understand how neutrons distribute themselves spatially in reactors. And that's going to be like one of the main things that we talk about today. But we're going to also go into trying to solve this equation in its current form. So try to solve for both the flux as a function of position and time. Um, and we had also talked about last time all of the different conditions that we need to solve this. And today is all about doing applications with this equation. So we will reinforce how you would, what those conditions are, and then how you would apply those conditions to various situations. And that'll allow us to get spatial distributions of neutrons in simple reactor geometries like spheres and cubes and cylinders. It'll Using this, we can start computing critical masses and critical volumes for those simple geometries. We can also start computing other interesting quantities like power peaking factors. And then, if time permits, we'll continue that discussion on to cases where you have multi-region systems instead of just a single region system. So the first way that we're going to start moving forward to try to tackle this problem is to look at it in its entirety. And in this equation, the flux, the scalar flux, is the variable that we are trying to solve for. And it's a function of both position and time. So that's what makes this a partial differential equation. And if you have a partial differential equation and you want to solve it, you basically have two options. Option one is try separation of variables. Option two is give up. So we're going to go with the first route, which would be separation of variables. When we talk about separation of variables, we're going to assume that the flux that we're trying to solve for, the scalar flux as a function of position and time, can be separated into two functions that separate the variables out. So we're going to assume that this looks like some r of r times some big T of t, where the R of R is our spatial shape function. It tells us about how the flux is, what the shape of that flux is. And then T of T is the time evolution function, which tells us kind of like it's a scalar multiplier that will increase or decrease to say how my flux is changing as time moves forward. And right now, neither of these functions really have any units attached to them, or at least the spatial shape function might have units, but in general, there will be a constant up front that kind of contains the flux, like the flux magnitude information. Because of the nature of this equation being a homogeneous equation, we can leave that constant out, and then we can just plug the constant back in at the end once we know something about our system, like once we know the reactor power or something like that. So that's why there's no constant up front, but that's okay. And what we're going to do is plug this definition into our one group diffusion equation. So what I wanted to do first is just compute what those partial derivatives look like into the terms where we have to like do a calculation with the flux, where the input is not just the flux by itself. Um, and so if we were to write this out with the definition that we've just defined, this would be d by dt of the r of r times the t of t. We're just plugging in this definition of flux into this time derivative. And so now we're taking a derivative with respect to time of two things, but one of those functions is just a shape function, so it has no time dependence. And if that r of r has no time dependence, then we can pull it out front of that d by dt operator since it doesn't depend on time. So this is equivalent to having r of r times the partial of big T with respect to little t. So that's what our d by dt term would look like once we make that substitution. And then the Laplacian on phi is kind of similar, where this is basically just saying take the Laplacian of that r of r times that t of t. And kind of similar argument here that what that Laplacian is basically telling you to do is take second derivatives with respect to space. And it kind of depends on what coordinate system you have, what the form of that Laplacian looks like, but it's always going to it's going to look like second derivatives with respect to x or y or z, or maybe second derivatives with respect to r if you have a sphere. The Laplacian does not do anything with respect to time. So just like here, we could pull out the shape function. Here, we can pull out the time evolution function because the Laplacian doesn't act on any variables that depend on time. So this is equivalent to pulling that spatial shape function out, and then we've still got the Laplacian now of that spatial shape function. The time evolution function came out from. So we can plug these definitions into the one group diffusion equation. And if we multiply both sides by v and then plug those definitions in, that's how we get here. This term right here is what we have on the left side. On the right-hand side, we are plugging in this definition here where we have the diffusion coefficient. So the t of t comes out, and then we have the Laplacian of that shape function. And then on the second term on the right-hand side, we just have that flux by itself. So when we plug the flux in, we just get that r of r times that t of t. That's generally kind of what separating variables in a partial differential equation sense would look like. And once we're there, we can hopefully move forward to get all of our variables on one side. At least get one side that's only a function of space and get one side that's only a function of time. And in this case, we can do that if we divide both sides by r of r and t of t. So if I do that on the left-hand side, then the r of r's are going to cancel. And what I'll have on the left side is just 1 over t of t. And then I've got that partial derivative of big T with respect to little t. When I plug that in when I divide both sides by r and t, the r's cancel, and I get a factor of that time. I get 1 over that time evolution function on the left side. And then on the right side, when I divide both sides by r of r and t of t, it's the t's that end up canceling. And then each term kind of picks up a factor of 1 over r. So on the right-hand side, I can write it like this, v over r of r. And then I'll have everything I have here except the time evolution part will have dropped out. So here I'll have the diffusion coefficient times the Laplacian of that shape function plus nu f sigma f minus sigma a also times, oh, and then here as well, I'm just going to keep the R of R inside. Technically, that R of R might cancel, but I've just kept that R of R on the outside. So like if you distribute it in, you would have a factor of 1 over R here, and then those two R's would cancel. But I'm just going to choose it to leave it like that. And this form is nice. That was kind of what we were hoping to see when we do separation of variables, is that notice how everything on the left-hand side just contains the time functions, and everything on the right-hand side just contains spatial functions and then constants. So mathematically, what this means is that like if time and position are both variables, then I could run through different values of time. Like if I knew what this time evolution function was, I could start computing what this left-hand side was at every time t. And like if I let t equal 0, I could get a number. If I let t equal 1, I could get a number. T equal 2, I would get a number. And because these two sides of the equation are equal, if I'm plugging in time values on the left-hand side, can anything be changing on the right-hand side if I'm only messing with time? The right-hand side doesn't depend on time, so if I'm changing the time values, the right-hand side is unchanged. And I can make a similar argument about if I started changing the space values. If I knew what the spatial shape function was and I started evaluating the right-hand side at different R positions, I could evaluate it R equals 0, R equals 1, R equals 2, and I would get different. The right-hand side might be changing, but the left-hand side doesn't depend on space. So the left-hand side doesn't change when I change my spatial variables. The right-hand side doesn't change when I change my time variables. And mathematically, the only way that can be true is if both sides of this equation are actually equal to a constant. And we're just going to call that constant because of convention. We're going to call it minus lambda. So that is what allows us to separate the problem into two different differential equations, where we're saying that the right-hand side is equal to a constant, the left-hand side is equal to a constant, and now we kind of have two differential equations that we can solve separately now that both of them are just a function of one variable. So that's the way, if you're lucky, that's the way separation of variables looks. If you try to do separation of variables on a PDE and you can't get something like this, it becomes a lot harder. You basically either have to like look at like tables of results, just like there's tables of integrals, there's tables of like partial differential equation solutions. You could also solve it numerically. But in this case, we can proceed forward by just doing this analytically. So if we look at what that if we look at what this spatial differential equation looks like, and we do some algebra to get it into this form, basically we could arrive here by just doing some algebra steps to make it look like the Laplacian times R plus a big constant times R equals 0. And for convenience, because we have this giant term right here, we're just going to let that be equal to a new constant that we call b squared, so that we can have this equation in a form that looks like something called the Helmholtz equation, which is a very common differential equation eigenvalue problem. So in general, what this Helmholtz equation is going to look like is that I've got the Laplacian of this shape function. And I'm going to do a subscript n here because this is an eigenvalue equation. So, and I'm going to write the b with a subscript n as well, and that's times r of r. And that's equal to 0. So that's kind of like what the form of this equation looks like if I substitute this in here for b, and then I recognize that this is an eigenvalue equation, which means that there's an infinite number of eigenfunctions and eigenvalues that would satisfy this equation. So that's my like new differential equation. And then to solve this differential equation, I need a boundary condition. We're going to keep using the same boundary equation that we had started with last time, which is that we're going to say that at the extrapolated boundary, our flux is 0. It means that we have a vacuum boundary condition. And so that means that this shape function evaluated at REXT, which is at the extrapolated boundary of my system, that this is equal to 0. And then this is an eigenvalue problem, so n can be any integer. It could be 1, it could be 2, it could be 3, all the way up to infinity. There's going to be an infinite number of these Rn and Bn pairs that satisfy this condition, or this equation. And so those R of R's, those are called the spatial eigenfunctions. Spatial eigenfunctions. And then those Bn squareds, those are the corresponding set of eigenvalues. And every because we had set this constant, we have this constant that we had introduced before, the lambda constant. Everything else that appears in this B equation is like a property either of the materials, or what the neutrons are doing. In that case, the nu F, the sigma A, and the diffusion coefficient are all like material properties. V is like the average speed of those neutrons, so that's kind of like a neutron property. Lambda was just a constant that we introduced. So every time that there's a different value of B, like B1, B2, B3, B4, every Bn is going to have a corresponding lambda n. So every set of Bn squareds leads to a corresponding set of lambda n's. And even though there's an infinite number of possible solutions that could satisfy this equation, we don't have to find all of them. There's only one eigenfunction that everywhere is going to be non-negative. And so we call that function that we care about R1. And it's going to have a corresponding eigenvalue B1 squared, which happens to be the smallest eigenvalue. And we give that eigenfunction that we are looking for a special name. That's called the fundamental mode eigenfunction. This is the fundamental mode eigenfunction. And ultimately, that's the eigenfunction that we want to find because you're going to have an infinite number of modes for this reactor, but only one of them is going to be everywhere non-negative. In other words, only one of them will satisfy the physical realizability conditions of the scalar flux, which means that the scalar flux can never be negative. Also, the scalar flux can't go to infinity. So that R of R, R1, in other words, is the function that we are looking for. So that's what R1 is called. That's what the eigenfunction we're looking for is called. B1 squared, the corresponding eigenvalue, also has a special name. We will often call that BG squared, and BG squared is the geometric buckling. B1 is the same as BG squared, which is what we call the let me erase that because that looks terrible. Geometric buckling. Based on those definitions, we can move forward. We can take the equation that we had before in terms of B and write it in terms of BG squared and then the corresponding lambda, which would be lambda 1. And we can factor out the V times the D on the left-hand side. And we can rewrite the equation in a form that looks like this. The reason that we write it like that is because this quantity next to BG squared has its own definition, and we call that BM squared, which is what we call the material buckling. So that thing next to the BG squared is what we call the material buckling. And that's what we call BM squared. The material buckling is our BM squared. So by definition, this thing right here is the material buckling. And then we can do a little bit of algebra on the material buckling to write it in different forms. We could take this material buckling and we could divide top and bottom by sigma A. So if we do that, we'll have nu F sigma F over sigma A. Oops. minus sigma A over sigma A all over D over sigma A. Just dividing top and bottom by sigma A. And then we're going to get some definitions that pop out of this. The first thing we have right here, nu F sigma F over sigma A, that's a special quantity in nuclear engineering that we defined, I think, last time or maybe the time before. That's our K infinity. That's the infinite multiplication factor. Sigma A over sigma A is just 1. And then this D over sigma A, we're by definition going to call this L squared. And so L, by definition, is the square root of D over sigma A. And this quantity L is what we call the diffusion length. This is the diffusion length. It's a length. The diffusion coefficient has units of like distance, and then the absorption cross section has units of 1 over distance. So overall, inside of the square root, I have like distance squared, and then the square root of a distance squared just gives me a normal distance. So the diffusion length has distance or length units like of centimeters. And physically, what that represents is on average how far a neutron would diffuse before it gets absorbed. So it is almost kind of like a mean free path in how and what the definition physically is, except instead of how far the neutron goes before a collision, it tells you how far the neutrons go before they get absorbed, how far they diffuse before they get absorbed. And so knowing that this quantity is bm squared and rewriting the expression for lambda 1 in terms of bm squared, we get something that looks like this on the bottom. And if we have this expression for that lambda, then we could go back to the differential equation that we were trying to solve, and we can actually solve that time evolution problem. So that this was that original, the time differential equation that we had, where this was just equal to a constant. And that constant we just showed was equal to this expression right here. So oh, there's supposed to be a negative sign. Sorry. There's supposed to be a negative sign in front of that. Because lambda 1 was just equal to this stuff, and then we had a negative up front from the definition. So just make sure you include that negative sign. And so this differential equation right here looks just like the differential equation that we saw for attenuation. It'll look very similar to the differential equation you get for like a radioactive decay problem. This is just a separable differential equation where we could like move the dt term over and integrate both sides. And what we would end up with is something that looks like an exponential. If we knew and with knowledge of this initial condition, then we can plug that in to get to eliminate the constant of integration that we get from that solving process. So if we go through the math, the solution to that is that our favorite exponential solution to a differential equation. And therefore, we have now figured out what the time part of our solution looks like. So now we can say that this scalar flux is going to be this spatial shape function. And I'm going to throw a constant up front now. So I'm going to have a flux magnitude up front times that shape function, and then times this time evolution function, which has an exponential of negative v times d times the quantity bg squared minus bm squared. And then that is a time function, so I got a little t for time inside of that exponential. Where kind of what I've done is taken this t0 and lumped it with the flux magnitude, which would be the thing that appears at the very front of our solution that gives it units that we would expect for a scalar flux. And so, oh yeah, and this R is technically R1, where that's the fundamental mode eigenfunction that we want to be plugging in for R, for our shape function. And so, depending on what the geometry is, you'll have a different value of the Laplacian, which will impact what that spatial shape function actually looks like. But then once we know what that shape function is, we can find what this flux magnitude is based on some other equation or some other quantity. Like if we know the reactor power or a fission rate or a leakage rate, then we can relate that quantity to this flux magnitude. And just like a heads up, sometimes in like Dr. Svedkov's notes, there's a different notation for this quantity. Sometimes it'll be called C of phi or A of phi. It represents the same thing, which is just a constant up front that gives us the magnitude of our shape function. Or sorry, the magnitude of our scalar flux. And so hopefully that is all good. And if this is what our time evolution function looks like, then we can study this a little bit more to talk about what characteristics would our system have if we want to talk about the system being supercritical or subcritical. So when we talk about criticality, it means that the loss and production operators are balanced. And so it also means that our flux doesn't change with time. So if we think about what's going to influence the time behavior of this of our system, it's based on our lambda one, and it's also based on this quantity right here. If the sign SIGN of these quantities is positive or negative or zero, that's going to affect what we have in the exponential, which is going to impact if our flux changes exponentially, like exponentially increasing or decreasing or steady with time. So if the material buckling is bigger than the geometric buckling, then this quantity right here, the BG squared minus BM squared, is negative. And that means I have a negative number times another negative number, which is going to give me an overall positive number inside of the exponential. And so, and also the sign of this term is going to match the sign of lambda 1. So if bm squared is greater than bg squared, then this quantity is negative, which means that lambda 1 is also negative. So in this case, lambda 1 is going to be negative. And I've got a negative times a negative inside of an exponential. So that means I have a positive exponential with time, which means that my neutron population, if that was my characteristics of my system, then my neutron population would increase exponentially, and that would mean that the system is supercritical. So if my material buckling is bigger than my geometric buckling, or my lambda 1 is negative, then I have a supercritical system. If these are exactly equal to each other, then I'm going to have a zero inside of the exponential, and e to the zero is a constant. It's one. So, and also if bm squared minus if bm squared equals bg squared, that means that this lambda 1 has to match that value, which would be zero. That means lambda 1 is zero, and in that case, our configuration is critical because we have e to the zero, which means that there's no time dependence. And that means that our neutron flux is going to be steady with time. And then the last kind of way that we could think about this would be if bg squared was greater than bm squared. And so in that case, now if bg squared is bigger than bm squared, then this quantity here becomes positive, which means lambda 1 is also positive. So that would mean lambda 1 is greater than 0. And if this quantity is positive, but I've got the negative up front, that means overall the exponential is negative, and that means that my neutron population would decrease exponentially with time, and that would be a subcritical configuration. Subcritical configuration. So the BG squared and the BM squared tell you about different things. The BG squared only depends on material properties. Sorry, the BG squared only depends on geometric properties, and the BM squared only depends on material properties. So the way that I kind of think about this is that your materials are ultimately what's going to like kind of dominate what if you can make a reactor critical or not. And if your reactor materials don't have a sufficient like fission rate to be able to sustain fission reactions and don't have an absorption that's so high that you have more absorptions than you have fissions. You basically need your materials to be able to sustain a fission reaction. Otherwise, the geometry kind of doesn't matter. So the material properties are kind of more important than the geometrical properties in that sense. Um, and then if your geometry properties kind of overpower your material properties, like you might have a system that can fission, but it's too big to actually allow for the chain reaction to continue, or maybe the geometry is such that it has so much leakage that it can't sustain that chain reaction. That's kind of what these quantities are telling you about. And if you want to make a reactor critical, then we need to find like the perfect marriage of our materials and our geometry such that the BM squared is exactly equal to the BG squared so that we can have a critical configuration. So when we talk about criticality conditions, we should be able to know different ways to talk about criticality. Like so far, we've talked about K equals 1 as being a way to know if our reactor is critical. This is another way that we can talk about the reactor being critical, these kind of internal definitions that we have right here. So, in general, though, we want to be able to talk about criticality in all these different kinds of ways. So, this, just like it would be very good for us to remember what does it mean if the multiplication factor is greater than or less than or equal to 1, we should also make a point to remember these different definitions of criticality too. Um, and so far, there's three different ways that we can talk about criticality in terms of the multiplication factor, in terms of how BG and BM squared compare, as well as what's our the sign of lambda 1. So yeah, that's a good thing to remember. That BG squared that we got from the Helmholtz equation does have, at least to an extent, it has a physical meaning. If we take that Helmholtz equation and get the Bn squared by itself, like we move the Laplacian over to the other side, and then we divide by R of n, then the Bn squared is going to look like this. It's going to look like negative 1 over R of R, Rn of R, times the Laplacian of that Rn of R. So whenever we think about first derivatives of a function, that kind of tells us about like the slope of the function. This Bn squared is going to be depending on the second derivative of this function. And the second derivative is what tells you about concavity or like the curvature of your function. So that's it. When we talk about B1, which is BG squared, that geometric buckling is kind of related to the second derivative of the original function, which means that it's related to the concavity of the function or how much that function is how much curvature it has or how much its shape is buckled. So this is an illustration of the first three eigenmodes, or like the first three eigenfunctions for the 1D slab geometry, where this is n equals 1, this is n equals 2, and then this guy right here is n equals 3. And you could do n equals 4 and 5 and 6, but showing the first three is also a good illustration of the fact that n2 could not be our fundamental mode eigenfunction because it has negative values, and our scalar flux can never be negative. Same thing with n3. n3 has negative values, and our scalar flux can never be negative within the domain of our reactor. So that's illustrating why, in this case, n1, which this is for a 1D slab, so it's a cosine profile is what that fundamental mode flux shape looks like. That hopefully helps illustrate why we could ignore those other fundamental mode, the other eigenmodes that are not the fundamental mode because they violate our physicality condition of the scalar flux. So in general, now what we want to do is find that fundamental mode eigenfunction. So I'm going to walk through how you can find that for a sphere. We're going to assume that we have a bare homogeneous sphere. So bare means that it's surrounded by vacuum. Homogeneous means that the sphere material is made of like one isotope. so it doesn't have multiple regions within it, like it's all fuel, for example. And we're going to assume that that sphere has an extrapolated radius, which we call big R with a little tilde up top. Um, so in general, when we're talking about finding a fundamental mode flux distribution, it kind of implies that that it's a steady state problem. In other words, that the shape function doesn't depend on time. And so the reason that we're starting with this form of the one group diffusion equation is because if it's the fundamental mode, that means that we're looking for like a critical configuration, and that means that the d by dt term has dropped out of the equation. It's like a steady state problem when you're looking for a fundamental mode flux distribution. So this would be the one group diffusion equation with the d by t term canceling out because it's in steady state. And then what I could do is it's common when you're solving these diffusion problems to group everything that has everything with a flux by itself together. So like if I were to move the sigma A term to the other side, and I would also move this d times grad phi term to the other side, and then I would divide out by the diffusion coefficient, then everything that's multiplying by phi by itself would end up being bm squared. And so this is just algebra and definitions to go from here to here. And then that's the form of the equation that's easier to deal with just because we only have one constant times a flux instead of having multiple terms where we could just factor everything that was attached to the flux out. So that's kind of what we've done here for that bm squared. And so this is our governing equation. And to solve this equation, we need conditions. Like, for example, we need to know what our boundary condition is. And in this case, because we said it's a bare sphere with this extrapolated outer radius, the extrapolated boundary condition means that our flux at that extrapolated radius is 0. If it's a vacuum boundary, then if we evaluate the flux at the extrapolated dimensions, there's a vacuum there, which means there's no neutron flux, so it's a 0. Yeah. So yeah, so basically, this is a when we write when we're solving for a fundamental mode flux distribution, it's a steady problem. So it's almost like if I go back to the original if I go to my original neutron diffusion equation, it's a steady problem, which means that this d by dt term goes to 0. So that's really why it was equal to 0, and then it was also equal to 0 because we just decided to move everything else to the other side. But yeah, if it's a fundamental mode problem where it kind of implies that it's a critical reactor or it's a steady state problem, so no time dependence, so that derivative with respect to time goes to 0. Good question, thank you. In terms of the physical realizability conditions, we basically just have to make sure that our scalar flux is bounded between 0 and infinity. And it can be equal to 0, but it cannot be equal to infinity. And this has to be true for all values of R that are within the domain of the reactor. So from R equals 0 all the way up to the extrapolated radius. Another way that you could say this is just for 0. Oh, so that's my physical realizability condition. That's going to be helpful for knowing which part of my general solution we can ignore. The initial condition for this problem, when we talk about initial condition, that is usually referring to the state of my system in terms of time. But because this is a steady problem, there is no initial condition. So we're just going to say none because this is a fundamental mode problem. That fundamental mode implies that we are critical, which implies no time dependence. So that's why you don't see any time dependence in these fundamental mode problems. Um, and then for moving forward, we need to spell out what the Laplacian is for this particular geometry. And in this case, because we have a sphere, um, then we can write out what the Laplacian is for a sphere. It looks like 1 over r squared times d by dr of the quantity r squared times d phi dr. That is what the Laplacian looks like for spheres. So that's what we can plug in to for the Laplacian to be able to move forward with the problem. The other kind of boundary condition that we could use, like you could use physical realizability for this problem, but you can also make use of the symmetry of the problem, which is that if we have like a symmetric geometric object, then that means that the flux is going to be highest in the center, and then it's going to decrease as you go towards your extrapolated boundary. And if the flux is highest in the center, it means that the derivative of the flux at the center has to be 0. So the other boundary condition that you could use is to just say that the derivative of the flux with respect to radius at r equals 0 is 0. Um, Two different ways that you can approach this problem. I'm going to show how we can do it with physical realizability because I think it's easier, but this is the other way that you could go about it. So at this point, we've satisfied and like spelled out everything we need mathematically to like start writing the differential equation and then solving it. So if I plug everything in and I write it as a Helmholtz problem, where I just use a subscript n instead of basically in this case we're saying that my flux is this Rn. Um, and then the constant that was multiplying by the shape function, because it's an eigenvalue problem, there's an infinite value of these shape functions that satisfy the equation, and there's a corresponding infinite number of eigenvalues that satisfy it. So this right here is like our full mathematical problem. And so when you have a differential equation like this, once you get to the point where you can look at the form of the differential equation, in general, what we kind of do, at least like in engineering classes, is we just say, we kind of recognize, you don't have to recognize every differential equation, but there's a couple of common forms of differential equations that come up again and again. And instead of having to like really solve them from scratch, you can look at the form and then recognize like, oh, my general solution looks like this, and then I figure out what constants I have or how I can simplify it from there. So in this case, if I have a differential equation of this form, then the known solution for my Rn is, oops, sorry, this is just R. It's going to look like a sum of sines and cosines, but because it's spherical coordinates, I get a 1 over r in the denominator. So it's going to look like C1 over r times sine of our bn times r, sorry, sine of bn times r, plus there's going to be a C2 over r times a cosine of bn times r. So that's the general form of this differential equation. And later on, I'm going to give you a big table that's helpful for the like 6 kinds of differential equations that we're likely to see what the known general form of those differential equations is. So it's like you look at the form, you match it to the table, and then you write the general form, which is what I've done here. So this is the general form of my the general form of the solution to this differential equation. And so what I need to do here is I need to think about what the forms of these two functions looks like so that I can try to eliminate one of my solutions. So if I look on this graph, the cosine of x over x is this red function, and the sine of x over x is this blue function. And so if I look at those two functions and then I think about physical realizability says that within the domain of my reactor, so from r equals 0 to the extrapolated radius, my flux can't go up to infinity. It also can't be negative. So if I look at the cosine function, notice that if this is r equals 0, notice that as r approaches 0 from the right, this cosine function goes to infinity. And also, as this function approaches 0 from the left, it approaches negative infinity. My flux cannot be infinity at r equals 0. Also, if I notice that, like, kind of getting further away, well, yeah, mostly for a problem like this, once I see that at 0, my um I'm violating physical realizability at 0, that is what allows us to eliminate this cosine function from my solution. I could basically just make the argument that C2 has to be 0 so that I don't have this part of my solution influencing what my flux does, because otherwise I could have my flux blowing up to infinity at 0. So because of physical realizability, I can eliminate the cosine part of my solution. And that means that my answer is just going to look like this sine function divided by r with a constant up front. So now I just need to find what my Bn is, which is going to be the next step. And so if I know that this is going to be my solution, then I can apply my boundary condition to this solution. So what we said with our boundary condition was that my function evaluated, so my function Rn evaluated at the extrapolated radius R tilde is 0. So that means that this left-hand side, what this implies that the left-hand side is equal to 0, and then I'm going to have a C1 divided by, I'm evaluating at R tilde. So everywhere where I see the little r, I replace it with R tilde. Right? The function is equal to 0 at that extrapolated radius, and I'm plugging in the extrapolated radius for R. Notice that from here, the C1 and the R tilde up front are just constants. So I could like multiply both sides by R tilde and divide both sides by C1, and those constants are just going to subtract out. So that means that really what I just have is 0 equals sine of Bn times R tilde. And so now I need to think about when is this sine function going to be equal to 0? And so if I think about like on a unit circle, if this is x and this is y, on a unit circle, the y coordinate is my sine function. And so if I'm here or if I'm here, those are the two places on the unit circle where the sine function is 0. And so that's like theta equals 0. This would be like theta equals pi. And then I could come back around. And so this could also be 2 pi. And I could keep going around in the circle a bunch of times. So this could also be 3 pi and 4 pi and 5 pi and 6 pi. So in other words, if the inside argument is any multiple of pi, then the sine function is equal to 0. So this is true. This is true if that Bn times the R tilde is equal to some integer multiple of pi. And we know that we're looking for the fundamental mode eigenvalue, which corresponds to B1, corresponds to n equals 1. And so if I have n equals 1, then my B1, um, my B1 is just going to be pi over R tilde. Plugging in n equals 1, the n is just a 1. I divide by R tilde, and that's what my B1 is. So if my B1 is pi over R, then by definition, B1 squared, which is BG squared, is going to be pi over r tilde all squared. From there, we get this. So this is what I get for a sphere. This is my BG squared, my geometric buckling for a sphere. Um, and that basically finishes our solution because Bn is for the fundamental mode, Bn is B1, which is this pi over r tilde squared. Or sorry, well, Bn by itself is just pi over r tilde. If I square it to get the buckling, then it's pi over r tilde squared. But the C1 is just a constant. That's going to get lumped with my flux magnitude so that if I wanted to say what my general solution is for this fundamental mode eigenfunction for a sphere, it's just going to look like this. This right here is what I get as like my final answer, where I'm just taking the constant of integration and lumping it with that flux magnitude constant, and that C phi is a constant that I would be able to find from some other auxiliary condition. Like if I know the total reactor power, or if I know a fission rate, then I'll have some other condition I could use to say what this constant is. So this is my eigen function or my fundamental mode eigen function for a sphere. This is the corresponding eigen value. And so if I were to plot this function with respect to r, I would get something that looks like this. So notice that at r equals, if this is r equals 0, that's where my function has its maximum. It has its maximum at r equals 0. And r equals 0 in this case corresponds to the geometric center of the sphere, corresponds to the sphere's geometric center. So at the geometric center, and hopefully that makes sense, right? The center is where you're furthest away from a boundary where neutrons could leak out. So at the center, you're going to have the highest like density of neutrons, and then that neutron density is going to drop off as you get closer to the boundaries where those neutrons could escape. So at 0, at the center is where my flux is the highest. Therefore, that's also where my fission density is the highest, because my fission density is just sigma f times the flux. And if it's a homogeneous problem, the sigma f is the same everywhere. So the fission density is going to be the highest wherever my flux is the highest, which is also at the center. So also at r equals 0. And then the fission density, that's where my energy is coming from, right? From all of these fission reactions. And so if I have the highest fission density at the center, that's also where I'm going to have the highest temperature. My highest temperatures are also going to be at r equals 0, at the center. So for all of these, and it's going to be the same conclusion for all of these fundamental mode eigenfunctions for simple geometric shapes. 0 is going to be where the highest flux is. That's going to mean that's where the highest temperature is. So if you have like a simple geometric reactor, the center is where you got to be worried about melting your fuel because that's where the flux is the highest. So hopefully that's okay. Um, I think Yeah. That's a good kind of walkthrough of doing separation of variables to kind of separate out and understand how the time evolution looks and how the shape function evolution looks. And then this is a good example of the process that you would go through to find the shape function for a simple geometry like a sphere. Um, you could do the same process for lots of other geometric shapes. And so this table 3.5.7.1.1 in Dr. Svedkov's notes. This is kind of summarizing the results that you would get for all of the other different geometric shapes. So we just did for a sphere, but all of these other geometric shape, and so notice this was what we found for the buckling, and this is what we found for our just the shape function by itself. And if you want to talk about the scalar flux, the fundamental mode scalar flux, it's just that shape function times your flux magnitude. So once you find that shape function, you multiply by the flux magnitude, and that gives you your scalar flux. And then, like I was saying, you can find that flux magnitude from some other auxiliary condition. Like if I say the reactor power is a number, then you can get an expression for this flux magnitude in terms of the reactor power. And so if you do it for an infinite slab, for like a rectangular reactor where the length and the width and the height are all different dimensions, um, for an infinite cylinder, which means that it's infinitely long in the z direction. Um, so there's no z dependence or h dependence, versus the finite cylinder where your flux shape can vary both with radius and with height. Um, in general, the sphere and also like the infinite slab or the cube are like the easiest geometries to deal with. Once we deal with cylinders, it gets a little bit harder because of the nature of those solutions. You get these J0 functions, which are Bessel functions. Um, but yeah, in general, you could go through that same process for any of these geometries to obtain these different relationships for the geometric bucklings and for the fundamental mode shape functions. And I'll talk about, we'll do a little example to see how, where these flux magnitude values are coming from. So if we want to talk about fission rate density for a reactor, if it's operating in its fundamental mode, then the flux only depends on position. And the fission rate density question? Oh, yeah. Um, it kind of depends. You will be asked to derive some of these on the problem sets. Um, and so depending on which question, like finite cylinder or even the infinite cylinder, it's a little bit trickier because of the it involving the Bessel function. But like this process that we just went through was only like 3 slides. So like I would hope that we could definitely do it for a sphere. Going through the notes and doing the same process on a slab. Slab is also not too difficult. Almost the exact same problem steps. You just have a different Laplacian for a slab. This would be a challenging derivation, but it wouldn't necessarily be outside of the scope. Maybe for the more complicated geometries, it would be. Um, and if not, like going through all the steps in detail, like in mathematically showing everything, at least being able to describe in words how you would go about it, those kinds of questions would be fair game. So this is the expression for the fission rate density. I'm just doing the macroscopic fission cross section times the scalar flux gives us the fission rate density. It has units of number of fissions per unit volume per unit time. And if we know the fission rate density and we know about how much energy gets released per fission, then we can put those two things together to convert the fission rate density into a power density. Um, do y'all remember about how much energy comes out of each fission reaction? Two, 200 MeV. 200 MeV per fission is the energy release, average energy released by fission. And so if the fission rate density has units of fissions per unit volume and per unit time, and I multiply by this average energy release, that gives me the definition of the power density. So I'll use Q triple prime for the power density, and it's just EF times sigma F times the flux. And so, and we can think about the units that the sigma F has units of fissions per neutron distance traveled. The scalar flux has units of neutron distance traveled per unit volume per unit time. And then the energy per fission has units of like MeV per fission. So notice that the fissions aren't a real unit, but if you track them, they cancel. The neutron path lengths also cancel. So now this is a quantity that has units of MeV per unit volume and per unit time. And so, and also if you think about the definition of power, that power is energy per time. Like 1 watt is 1 joule per second, and watts are like the SI unit of power. So over here we have MeV per second, and MeV is also a unit of energy. So MeV per second, that's a unit for power. It's a unit of power. And like ideally, you would use a conversion factor to convert the MeV into joules, so that you would have the power in joules per second, which would be watts. But in general, this works out to give us a quantity that has units of power per unit volume. And power per unit volume is what makes it a power density. So this right here is our expression for the power density. And if power density is power per unit volume, then if I take that power density and I integrate it over the entire volume, that gives me the total power produced by the reactor. So PF is the symbol that we use for reactor power. And it's just the integral over the volume of our power density, integrating with respect to volume. And so this is the volume of the core, or whatever part of the core is producing power. I think that's an important thing to make sure that we're aware of, is that like if you had a multi-region reactor where it was like fuel and then a reflector and then fuel and then another reflector, the power would only be due to the parts of the reactor where you had fuel, where you were producing power. And then, you can sub in the definition that we just introduced to say that this is the integral over the core volume of EF times sigma F times our phi of R dV. Just subbing in the definition for power density in here. And then this phi of R, that's going to be different for every fundamental, that's going to have a different fundamental mode flux shape for every geometry. So if depending on what the geometry is, you could also look at this as a volume integral. We've got an EF, we've got a sigma F, and we could just replace this flux, the scalar flux, with a flux magnitude times that shape function. Just different ways of writing the same thing. Fundamentally, that's kind of like probably where you would start if you had a given problem. Like if I said, find the reactor power for a sphere, then this shape function would be for a sphere. And then based on what that function looks like, you would have a different dv, right? The dv is going to be different depending on what coordinate system you're in. Like if it's rectangular coordinates versus cylindrical coordinates versus spherical coordinates, there's a different form for the dv. So this is the definition that you could use to then get those C-phi values that you see in this table. And that's fundamentally where these C-phis are coming from. It's assuming that you know the reactor power, and then you carry out this integration to get an expression for what that reactor power looks like in terms of in terms of these cross sections, and in terms of the integral form of this shape function. So we should definitely be comfortable with obtaining these flux magnitudes, which means that we should be comfortable integrating these spatial shape functions over the volume described by the geometry. And I gave you guys some practice on that on the second problem set, and I was going to kind of talk about at least walking through the steps for what that would look like for a sphere. So this is what Dr. Svedkov's notes say that flux constant is. If you know the reactor power, find the flux magnitude is like kind of what the problem would say. So we start with that definition of reactor power that we just wrote down. And then we recognize that we could further rewrite the flux as that flux magnitude times the shape function. And then the EF, the sigma F, and that flux magnitude are all constants that can come out of the integral. So that's how I get here is I've just pulled all the constants up front, and then now all I'm doing is integrating that shape function over the reactor volume, where this is the shape function for this geometry, which was a sphere. And so we already saw that that shape function looks like 1 over r times sine of pi r over big R tilde. That's the shape function for a sphere. And then if I want to carry out this integration, I got to plug this in for R1, but I also need to know what dV is for a sphere. Do y'all remember what dV is for a sphere? If you're in spherical coordinates, what's that differential volume look like? Kinda. Okay, let's back up. Do we know the formula for the volume of a sphere? Perfect. Okay, let's start there. 4 over 3 pi r cubed, right? That's the volume of a sphere. That's something that we should have memorized. If we don't have it memorized, it's a really good one to have memorized. Because if you remember this, you can get dV for a sphere. The way I would get dV is I would take the derivative of this with respect to r. So if I take the derivative of this with respect to r, it's just a power rule, right? This 3 comes down, those 3's cancel, this r goes down by 1, so it becomes 4 pi r squared, right? And so my dv is just, I just multiply the dr into the other side, so my dv is 4 pi r squared dr. That's my dv for a sphere. So if that's dV for a sphere and that's my spatial shape function, then I can plug that all in right here so that my PF is going to look like C of phi times EF times sigma F times the integral of 1 over R sine of pi R over big R multiplied by dV, which was 4 pi R squared dr. And so when we're integrating over the power producing region, we're integrating over the volume of the sphere. And if now we've written the integral in terms of r, so it's going to go from r equals 0 to r equals the extrapolated radius, which was that r tilde. And then notice that this 4 pi can come out front because it's also a constant. And then also one of these r's can cancel one of these other r's, right? This r can cancel with one of these r's here. So this is going to end up looking like 4 pi times C phi times EF times sigma F times a integral from 0 to big R of R sine pi R over big R tilde D. Yeah. And so that right there, if we were to carry out this integration, we should obtain the result for the fission power, which like if we end up carrying through all of this and you do the integration right, you should get 4 pi times times C phi times EF times sigma F, and then you get an extra factor of R tilde squared over pi. So if you go through that integration, that would be what you get for the power. It's going to look like this. And then to get C phi, you would just rearrange, right? So if I divide both sides by 4 pi and I divide all this other stuff to the other side, that's where that comes from. It's taking that integral and then rearranging terms. So that would be how you could get that flux magnitude based on the reactor power and then based on like the material and geometric properties of that reactor. And so this is a question that is given on, it says homework, it's just on the second practice set of problems. Um, this is and if I was going to integrate this, it's just integration by parts because I've got like a two functions being multiplied together. Um, Being comfortable with integration by parts is highly recommended because this would be a really good question for me to ask on an exam to like derive the flux magnitude for a sphere. Or yeah, which would involve carrying out these kinds of integrations. So that was why I was saying definitely good that we can do the integrations of these shape functions over the volume. Um, yeah, very likely that I would ask something like that on an exam. And if you go through those practice problems in the homework, that'll get you through pretty much anything that I would ask on the exams. So in general, that's the practice problems are really important in that is how we get practice. That's how we make use. Like if you're in class and you're following along, but then you don't think about or practice any of the stuff that you learned, it's your knowledge is just like an exponential decay function that's like going to zero with time that you don't practice. So practicing is really important, and practicing as soon as you can after you like learn something or see it is important too, because the longer we wait, the more that we forget. Even if we think that we're going to remember everything that Mr. Simonian said in the lecture, there's going to be stuff that we forget. There's also stuff that to learn, you just kind of have to go through like the friction and the tediousness of like going through the steps. There's kind that part of it is kind of unavoidable. So starting as soon as we can, very helpful so that we make sure that we're getting practice and so that we're like building the skills that we need to have to be successful on the quizzes and on the exam. Um, so kind of connecting what we've been talking about with just like a practical example, thinking about a large AP1000 reactor. The AP1000 is like the newest reactors that we've built in the United States. Um, I really like the AP1000s. I think they're really cool. The AP1000s, they look a little bit different. Like when you see containment buildings, they normally have that normal, like kind of curved dome shape. These containment buildings, you can tell the difference because they have this little hat on the top of the containment. And within this hat, there's like multiple Olympic swimming pools worth of water that's just stored at the top so that if they have some kind of like loss of power accident, they don't have to pump water in. They just open some valves that allows that water to like dump onto the core or into the systems themselves so that you don't have to rely on like pumps in emergency situations. And that's enough power to passively cool the reactor for like a couple of days, which makes a lot of difference in terms of like emergency response and getting backup power turned back on and stuff like that. So it's the AP1000, which means that it has a rated electric power of 1,000 megawatts. The thermal power is a lot more because of the thermal power is the total heat that you generate, but then there's efficiencies or inefficiencies in the thermodynamic process by which you can only extract a certain amount of that. So what is produced by fission is the thermal power, which is about 3,400 megawatts. So if the thermal power is 3,400 megawatts and the energy per fission is 200 MeV per fission, then we can relate those two things to approximate what the fission rate of the reactor is. So the fission rate is going to be approximately that thermal power divided by the energy per fission. So I've got 3,400 megawatts for the thermal power divided by an energy per fission of 200 MeV per fission. And so the units on top and bottom need to be reconciled because I have units of watts and then I have units of MeV in the bottom. So if I convert the MeV into joules with the appropriate conversion factors, then what this comes out to is about 10 to the 20 fission reactions per second. So that's like an estimate for the fission rate in a large nuclear reactor. 10 to the 20 fissions per second, or if you were to write it out, it's a 1 followed by 20 zeros of fissions happening per second. So just like our brains have a hard time comprehending numbers that are that big, but like very huge number. And all of that energy in that reactor is generated within the reactor's fuel. All of these fissions are happening in the fuel of the reactor, and all of that energy comes out in the form of heat. Every single time a fission reaction goes off, you've got two fission fragments that are separating from each other. They're stopping in a very short distance and basically depositing all of that kinetic energy they had into heat, into that reactor fuel. And you have 10 to the 20 of those fission reactions happening every single second. Um, if this reactor is critical, then the flux of the reactor is going to vary with position within the reactor. So that flux and therefore the power density is going to vary with position. And we already saw that the flux and therefore the fission density are going to peak in the reactor's center. And so at the center is where we are going to have the highest temperatures. At least for like a one region reactor, the flux is going to, this is all true for a one region reactor. And generally it's true for large reactors too. Yeah, basically that's where we have the highest temperature. And if that's where we have the highest temperature, that's where we have the highest chance of melting our fuel. And so in terms of like kind of thermal limits of our reactor. It's the melting point of the fuel. If you ever exceed the melting point of your fuel, you're in big trouble. And so this kind of phenomena and the fact that there's a location in our reactor that's going to be hotter than the other parts of our reactor leads us to the concept of the power peaking factor. And the power peaking factor, just by definition, is a ratio of the maximum power density that you could have in your reactor divided by the average power density in the core of the reactor. So the maximum power density, you can find that, we're going to say Q triple prime max for that maximum power density. And then the average power density, we're going to say Q triple prime with a little overbar. And the maximum, we're going to find that by just evaluating, we're just going to evaluate Q triple prime at the center. Depending on what the geometry is, you'll have different forms for this Q triple prime. But if you just evaluate it at the center, that is by definition going to be where your power density is the highest. And then the average power density is kind of like a mathematical definition that if you're taking the average of this power density, it means that you're doing 1 over the volume of your core, and then you're integrating over the volume of the core of your original power density. That's kind of what it means to take the average, at least like in a calculus sense. An average of a quantity means integrate that quantity over the whole domain and then divide by the thing that you're, in this case, because it's the power density and we're integrating over the volume, then we end up dividing by the volume to make it an average. So that's the definition for the average power density. That's how you can find the maximum power density. And if you take the ratio of those two things, that's how you can get the power peaking factor for any simple geometry. So just like there's a list of those CFEs for every kind of geometric shape, there's also a list of power peaking factors for every shape. This table comes from, this is table 5.4.1 from Dr. Svetkov's notes. And so it contains, this is the result that you would get, oops, this is the result that you would get if you carried through that definition for the power peaking factors of all of those different geometries. On the second problem set, there's a question that asks you to derive some of these. Sorry. That's something that we should be able to do. Like possible exam question would be deriving these kinds of power peaking factors, which means that it might look scary, but it basically just means, again, we need to know how to take volume integrals of the power density. But remember, the power density is basically just EF times sigma F times that shape function. So really, we just need to be comfortable with integrating those shape functions over the volume, and then you can answer questions about the flux magnitude or about the power density. So we've talked a lot about different forms of the criticality condition, and I just wanted to remind us that we can also continue talking about K effective in this context. So like if we took our steady one group diffusion equation, but then wrote it as an eigenvalue problem, it would look like this. And we can then get it in the form of a Helmholtz equation by lumping everything that depends on the flux together, uh, and then putting all those constants together and calling that Bn squared. So in this case, if I were to move everything over and then factor out all the stuff that the phi is attached to, this multiplying constant would end up looking like this. And so this form of Bn squared can be used to write an expression for K based on these new properties that we've talked about. So it's like, if this is my definition for Bn in terms of all of these quantities, I could then do algebra to get Kn by itself. And there's a couple different forms that that would look like. The first one, it would look like nu f sigma f over sigma a. And then all of that is over 1 plus L squared times Bn squared. Doing some algebra to get Kn by itself would lead me to something that looks like this. I can simplify this a little bit further because, again, this nu f sigma f over sigma a is a definition that we recognize as the infinite multiplication factor. So that's the same thing as K infinity over 1 plus L squared Bn squared. And I could have also taken this original definition and I could have multiplied top and bottom by sigma a so that this sigma a cancels. This becomes sigma a. This becomes L squared times sigma a, which I can rearrange and to be expressed in terms of the diffusion coefficient. So the other way that this could look is nu f sigma f over sigma a plus the diffusion coefficient times Bn squared. So those are like the different ways that I could express this multiplication factor as an eigenvalue in terms of these other quantities, including the original eigenvalue of the Helmholtz problem. So just like there was a pair of B ends and lambda ends that went together. There, in this context, there's a pair of K ends and lambda ends, sorry, K ends and B ends that go together. And if we write this in terms of the fundamental mode, which means n equals 1, and that corresponds to K effective, then I could say K1 is K effective, which is K infinity over 1 plus L squared. And then if we're plugging in n equals 1, that means B1 becomes BG squared. And that is also the same as writing this in terms of nu f and sigma f, that I would have nu f sigma f over sigma a plus the diffusion coefficient times BG squared. So these are our one group diffusion approximations for K effective. And so in this case, notice that K effective, it depends on material properties, which is like the nu F, the sigma F, and the sigma A, but it also depends, and the diffusion coefficient, but it also depends on BG squared, which is going to be based on the geometry. So it's like a balance of production and loss, including both the material properties and the geometric properties of the system. Um, if we now have some expressions for talking about critical reactors, then we can write a statement of criticality and then use the definitions for like BG squared for our different geometric shapes to better understand what would be the critical dimensions or how to basically design a critical reactor of comprised of these simple geometric shapes. So like in general, if we want to talk about what is a critical system, the newest one of the new definitions that we've learned is it means that BG squared equals BM squared. So this is like a good starting point for finding critical geometries or critical configurations, where BG squared is all based on geometric properties. Um, so like if I just go back to our table real quick, notice that these BG squareds only depend on the dimensions of our reactor. Like the A, B, C would be the lengths in XYZ coordinates. R and H would be the radius and the height in cylindrical coordinates, and then R is the radius in spherical coordinates. So these bucklings only depend on the geometries. That's why it's a BG squared. It's based on the geometry. And then we have a definition for BM squared, and that only depends on material properties. Um, and so depending on what your shape is, you're going to have a ability to relate BG to the geometry in ways that are either easier or more challenging. If it's a sphere, then this is my BG squared. And so my BG squared only depends on one variable, like one length dimension. Same thing if I have a cube, it's only going to depend on one dimension, which is the side length of the cube. And that makes it pretty easy to determine what my critical like dimensions in terms of a volume are, because I could just plug in this definition for BG squared. I'll have a definition for BM squared based on my material properties, and then I'll just have one unknown that I need to solve for. Like if I solve for the radius, then I can get my critical radius, and then I can turn that into a volume by using the volume of a sphere. Same thing with the cube. If I can plug this in here for BG squared, I know what my material properties are. I can get A by itself. And if I get the side length of that cube by itself, then that's like the critical dimension of the cube. And if I take the volume of the cube by doing A cubed, then I can get the critical volume of that configuration. So if it's a sphere or a cube, very easy to get those critical dimensions because there's only one dimension that I have to find. Um, and so, but in general, we can talk about these different shapes and which shapes are the best in terms of comprising a critical mass. So if I want to find the minimum critical volume for these different geometries, it's basically going to depend on the material properties, but it's also going to depend on the characteristics of that shape, which is going to be about the most important thing for these simple shapes is just the surface to volume ratio. If the surface to volume ratio basically gives you a measure of how much leakage you can have out of your system. And if your surface to volume ratio is small, then it's harder to leak out of that system. And if the surface to volume, if the surface is very large compared to the volume, you're going to have a lot of leakage. If the surface area is small compared to the volume, you're going to have less leakage. So the shape that has the best surface to volume ratio is also the shape that's going to have the minimum critical volume. And in this case, the sphere is the best way to make a critical configuration. So if I talk about the minimum volume for a sphere is the smallest that I can get. The next most efficient would be a cylinder. So that compared to the volume minimum for a cylinder. And then the worst would be, in this case, a cube. So the volume minimum for a cube. The cube is going to have the largest volume. The sphere is going to have the smallest volume. And so that's why if we're trying to make a critical mass with the least amount of material, we're pretty much always going to pick a sphere. Um, so the geometry makes a difference in terms of which shape is the most efficient, but also the composition matters too. This is illustrating how if you have different spheres composed of different nuclei, that the more efficient material can have an even smaller critical mass. So plutonium-239 can make the smallest critical sphere, whereas uranium-233 would be bigger, and then uranium-233 would be like kind of somewhere in the middle. Um, so that's and these definitions come from just finding the critical volume of the sphere. And then if you need to, doing a minimization problem, depending on what the kind of what volume you have or what the geometry is. So like I'm gonna walk through just the kind of steps that you would follow for doing this for a cylinder, because the cylinder is kind of a little bit harder because it has two dimensions that you have to keep track of. Um, so if we talk about a cylindrical reactor, then there's a BG squared for a cylinder, and it looks like 2.405 over R tilde squared plus pi over H tilde squared. So that's the definition of the geometric buckling for a finite cylinder. Notice that if I say that this BG squared, if it's critical, then it's equal to the BM squared of our reactor, if critical. Then this BM, there's basically two different values of R. In terms of the geometry, it depends on R and it depends on H. So if this BM squared is a certain number, that means that BG squared is a certain number. Like if it's critical, they have to be the same. But if my BG squared is constant, there's an infinite combinations of R and H that I could pick that would give me that corresponding BG squared. So like in general, what I would do in terms of an optimization problem is I would just write that criticality condition, which is that BM squared equals BG squared. And then I would take where I have BG squared, I would use the definition. Yeah, I would use the definition of BG squared to write it in terms of those two dimensions. That would give me an equation that looks like that basically just looks like this. And then from there, I have two unknowns, R and H. The way that I could eliminate an unknown is I could use the formula for the volume of a cylinder so that I can write my BG squared in terms of one variable. Like I could take this definition and I could get R as a function of H, or I could get H as a function of R, and then I could plug that in for one of those variables so that I turn it from a problem that depends on two dimensions to a problem that just depends on one dimension. And then in my equation, I'll have the volume, I'll have the BM squared, and then I'll have one dimension, either the height or the radius. And once I'm there, if I want to find the minimum volume, then I do like a first derivative test on that volume function. I take that volume, take its derivative with respect to whatever variable I've left, like take the derivative with respect to R or with respect to H. And then in that first derivative test, you take the derivative and then you find what values of the input make that derivative be equal to zero. And that would tell you about the dimension that you solve for that would minimize the volume. So you would find like the R minimum or the H minimum. And then once you know what that value is, you could plug it back into your equation up here. And then that would give you that would allow you to find the critical dimension of your system. Because now, yeah, you would be able to do things individually. Um, and so that's kind of that's the approach that I went through when I was finding the critical dimensions of those different shapes. In Dr. Svedkov's notes, he also talks about using Lagrange multipliers, but I think the Lagrange multipliers are kind of like a it's kind of like overkill method for something like this. But yeah, those are kind of the steps that I went through. I think those are the steps that make the most sense. It also is kind of helping us refresh our knowledge of like using the first derivative test, thinking about like calculus one kind of stuff. So that's kind of the main stuff that I wanted to say about single region systems. And now that we've kind of laid the groundwork for one group diffusion in the context of single region systems, we can start talking about multi-dimensional systems. So like if you think about a real reactor, it's not just one material, it's not just fuel. In a real reactor, like this is a simplified model of a reactor, but it's more accurate in that you've got fuel, you've got like a coolant, like maybe it's water or some kind of gas. Maybe you've got a moderating material like graphite, or yttrium carbide or something else. You've got control rods that can control the reaction, that can add absorption if you need to shut the reaction down. So this is an example of a real reactor, and all real reactors are multi-region systems. All real reactors are multi-region systems. So there's a lot of different materials in there. The materials are going to have different properties, right? Like steel and water and fuel are all going to have different cross sections, different diffusion coefficients. And so what we will generally assume is that within each region, like if I have a fuel region or if I have a control rod region, that within that region, my material properties are uniform. Material properties are uniform, but then we can allow those properties to vary from region to region. So everywhere where there's water, it would be a constant material properties. Everywhere where there's uranium, it would be constant material properties, but they are different material properties for different regions. And so in that sense, if I want to use the diffusion coefficient to solve for the flux distribution in a multi-region system, all I really have to do is just solve the one group diffusion equation in each region. I'm going to say solve the one group diffusion equation in each region. And then once I've solved or at least written like a general solution for the one group diffusion equation in each region, I can match the solutions in each region using interface conditions. So that's kind of where that's the multi-region problems is where those interface conditions are gonna pop up. We didn't need them before because we just had a one region problem. So you have no real interface. You just have an outer boundary. But if you have two regions, like if you have an inner core with an outer reflector, then you've got a fuel region, you've got a reflector region. You can write the one group diffusion equation for each of those separate regions. And then you can link the solutions to those regions by using interface conditions. So this is kind of like just getting us thinking about the terminology for a multi-region reactor problem, where in this case, we've got two volumes. V1 is the volume of one material region, like maybe that's my fuel, and then V2 is my other material region, maybe that's a reflect. And so in region one, I have all of these I have material properties for that region, and I'm using the superscript one to denote quantities that belong to region one. And then I'm using the superscript two for quantities that involve region two. And then for each region, it's going to have its own boundary conditions, like depending on what the problem looks like. Each region can have boundary conditions. We use this dvext to define the extrapolated boundary. So that's in this picture right here. If I look at like just the outside of this problem, that is the extrapolated volume. And now there's a interface surface between these two regions. So that's like kind of what this gray highlighted region is right here. This would be the surface over which those two regions are touching. And so, and that's what's illustrated as a straight line right here. That's the line or the interface between region one and region two. And so at that region interface, there's a unit normal that just points outward, perpendicular to that surface. And that's the E hat N, and it's at some location R int, which is the interface location. And so I think I have time just to get through this one slide, which is basically just reminding us that this is the one group diffusion equation. I'm now just writing it as a multi-region equation. So I have a superscript I on my flux, and I have a and I could have superscripts I on my properties too, because basically what this is saying is that within every region, I will have a different solution for my flux. I would still have a boundary condition, like I'm still going to use vacuum boundary condition at the outside of my geometry. If this is a time-dependent problem, I would need my initial conditions too. And then my interface conditions are what I have to match at the interface. And for my flux solutions to make sense, I need for there to be continuity of the scalar flux. Oh, okay. I guess I didn't have as much time as I thought. We'll pick up on this slide next time. We'll talk about interface conditions, and then we'll talk about solving the criticality problem for a multi-region reactor. Um, so that was all I had for y'all today. Thank you for your time. As always, if y'all have questions or if you need help with any